Hi guys, Daniele here. Today we're going to talk about Risset accelerando and rallentando, which is an auditory illusion very much connected to the Risset glissando. Some of you might already know what a Risset glissando is. If you don't, it's an auditory illusion where a tone keeps rising up or falling down indefinitely, and it is achieved by means of having partials distanced by octaves and whose power is distributed around a central frequency, so that those partial comes from nothing when they are very low in frequency and goes to nothing when they are very high in frequency, and everything is synced up so that all these partial keep rising up and keep going up. The Risset glissando is very much connected again to the Shepherd scale. Again, you can Google it and you can discover more if you don't already know what this is. Risset accelerando e rallentando is pretty much the same as the Risset glissando, only for rhythms instead of frequencies. We have rates instead of frequencies in a sense. But it's gonna be the same. There's a key difference. We're gonna take care of phases along with frequencies and amplitudes because it's gonna be key to get all the phases in sync. It wasn't that important in a Risset glissando. It is in a Risset rhythm. The hardest part will be to get our math straight, but we are in luck because Dan Stowell did it for us. We're gonna base our analysis on this very nice article titled "Scheduling and Composing with Risset Eternal Accelerando Rhythms" by Dan Stowell, indeed. And he did the math for us. We're gonna use his math. However, if you're interested to know where the equations come from, you can look up the article online. I'll put a link in the description. It's worth the effort. I think if you know a little bit of calculus, you can get there. It's really not that hard. The basic scheme of what a Risset accelerando is not very much different from the one for the Risset glissando. So we have partial rising up, always in sync with each other, at octaves apart, spaced by octaves. Only these are not frequencies, these are speed rate. And speed rate of what? Well, the basic idea is to have a source buffer. It could be a source audio buffer, it could be a source score buffer, and we're gonna use a source score buffer because we're gonna use the Bach and Cage libraries, so we're gonna do it with symbols, with scores, and not with audio, but it's gonna be the same thing essentially. There's a buffer, and this buffer is actually sped up by a speed rate factor represented by those lines always in sync and always going up. Those are the partials, those are the rhythmic partials. And then the sawtooth lines are actually just representing the phase inside each of the buffer rating. So we read the buffer once, there's just one phase. We read the buffer twice. This is the phase from the beginning to the buffer to the end of the buffer, from the beginning to the end, from the beginning to the end, and so on and so on. Again, the amplitude of each one of the partials is going to be proportional, is going to be modulated by some sort of bell-like curve around a central rate. And it goes down at the top, it goes down at the bottom. This assures that our rhythmic glissandi, our rhythmic accelerandi and rallentandi will always be seamlessly, eternally going up, well, speeding up, let's say, or slowing down. This is the speeding up case, of course, where frequencies go up, rates go up and up and up. So the main problem is to get those quantity right. And the quantities we need to get right are the speed rate, how fast are we reading each buffer at each moment, the central rate for amplitude, t and tau. Well, t is easy. T is just the duration of the buffer. Tau is a bit different. It's not just the duration of the buffer. You see that in this kind of scheme, that Dan Stowell proposes, what happens is that the buffer is in sync, gets in sync again after a certain amount of time. So we read the buffer once and then everything gets in sync. We read the buffer twice in this layer and everything is in sync. Layers are the things shown in these kind of parallelograms stacked up vertically, and partials are sort of a sequence of layers. This duration where things get in sync anew is called a metabar, and tau is the duration of this metabar. In principle, it could be something else than t. Don't let be fooled. This seems like a sort of diagonal or something. It's not, because the logical times should be in a sort of third dimension or something. But I just used the same diagram that Dan Stowell did, so this is borrowed from him and modified a little bit. So this t is in another dimension in a sense, and this is crucial. This is some sort of logical time, the time of the original score. It may or may not have to do with the elapsed time. In this case, it's not the same because it can be sped up by the variable speed rate. So we have a logical time, the position in milliseconds in the original score, and we have an elapsed time, which is the actual time of the overall process. Let's say the time in the destination score, in a sense. It'll be key to see how the two are related. This is going to be key. And as I said, Dan did it for us. Those are the key relationships we are going to use. The first three are exactly as Dan Stowell derived them. Especially we are going to need these one, the TE1, and possibly the TL. The TE and the T, those two are exactly the same. Just one is the inverse of the other. So TL in function as a function of TE, and TE as a function of TL. This is the equation deriving the rate for each point in the elapsed score. This is the rate. And for each layer V, this is going to be crucial. We're going to take V into account. It depends on the layer. It depends on the partial. Again, V shows up in these equation as well. The last one is just a bell-like curve to map the amplitude at the end. I think that this is not the one Dan Stowell used. He used a cosine, but it's going to be pretty much the same, so I'm going to use a Gaussian curve. This is the Gaussian curve. Very well. Let's get started. Let's create a new patch, and in this new patch, let's take a bach.roll as a source. This is going to be our buffer. We're going to put music in it. It's going to be our source buffer, our music. Let's put the ruler on. Let's display the ruler above, and let's display the ruler labels as well. Here we go, so we can see how much time is represented in the buffer. And let's just put a single note for now. It doesn't really matter. We will explore it later. Let's make it a bit longer, say around 2 seconds something. Doesn't really matter. Again, we can modify this later. What we need to do is to build one of the metabars and then replicate it a certain number of times. Okay? So, how do we build a metabar? Well, we build each of the partials, each of the layers. Each layer is represented by a letter V. V equals 0, V equals 1, V equals 2, V equals 3, V equals 4. So we're going to do that. Before doing that, however, let's get some of our parameters in place, because there are a few parameters we need to define. For instance, we need to define, well, the number of layers we want to use, or the number of metabars we want to replicate. Let's call L the number of layers, and we use bach.eval for that. Bach.eval is a window for a programming language named Bell. It's very powerful and it works seamlessly in the with Bach LLLs, but in this case we are not going to use it to its fullest potential. We are going to use it because it can define variables and use them in the computation. So we're going to use that feature, which is handy. So let's say we have, I don't know, 7 layers, and we have 20 metabars. It's just going to be the number of copy pasted metabars. So 7 layer, 20 metabars, and let's define the central rate for the amplitude bell curve to 8. Again, you can explore later. We can put spaces or not put spaces, it really doesn't matter. The last thing we have to define is the sigma, which is the standard deviation for the bell curve in the amplitude mapping. Let's put it to 1.5. You can again experiment to whatever you wish. And let's say at auto 1, if we do that, those variables are already defined when I instantiate the object, which is handy. Now I know that these variables have these values. As you see, the sigma is at the denominator of this fraction. It's really the standard deviation of this distribution, which means that the higher the sigma is, the slower the bell-like curve goes down at the extremes. There's one more thing we need to do. We need to set. The thing we need to set is the duration t of the buffer and the duration tau of the metabar. They don't need to be the same necessarily, but in this case I will put them equal to each other. You can experiment again with other values, but they don't need to be exactly the same. As t, the duration of the buffer, well, it could be actually the duration of the score. We can take it with the get length. This is gonna give us the duration of the score. Let's put a bach.keys length here to retrieve the length of the score. And let's give it to both variables t and tau. We can also do that. So it's gonna be assigned to both. Very well. We're gonna use it an integer duration in milliseconds. You can use a floating one, it doesn't really matter. Now we have to build each one of the layers, each one of these 1, 2, 3, 4, 5 up to L layers. So we need an UZ. It would be nice to have this, but of course UZ doesn't know about the variable L. So let's put something. It doesn't really matter what we put here because we're going to use bach.eval L .m in order to retrieve the L value and produce L numbers from 0 to L minus 1 coming from here. Those are the indices of the layers we have to build. For each of the layer, we have to read the buffer a certain number of times. The first layer is just once, 2 to the 0. The second layer is twice, 2 to the 1. The third layer is 4 times, 2 to the 2. And you see the pattern is 2 to the 2 time, 2 to the v time. So let's do something nice. Let's put this variable to v. We assign the variable. And then let's replicate. So let's repeat this score 2 to the v times. How do we do that? Well, let's use cage. Cage.repeat is very handy in these cases. It repeats a bach.roll or a bach.score a certain number of times. How many times? Well, 2 to the v. So again, let's use bach.eval for that. 2 to the v. It's nice because we can use bach.eval like a bach.expr with additional variable capabilities. So we can use variables inside that. We can use a trigger if we want. And first thing we define v. Then we can do that. It doesn't really matter. We are doing a bit more get length stuff than needed, but it's not gonna be our bottleneck, so let's keep it like that. It's gonna be easier, and you can optimize the patch if you want later. We dump the score and we reproduce it a certain number of times. Well, 2 to the v, we just need a trigger here. Doesn't really matter. Here we go. Very good. Once we have repeated the score 2 to the v times, we have to speed it up. From where to where, and with which equation? Well, to speed up something, in general, to warp the time of something, we use cage.time warp. Cage.time warp is handy because in its basic format, well, its basic functionality is to define a warping function via a lambda loop. This lambda loop spits out the logical time, the time in the original score, and expect to receive the elapsed time, the time in the final score. This is handy because we have a formula for that. This is the formula, you see, from logical time to elapsed time. So all we need to do is to apply the formula and to put it in a lambda loop. How do we do that? Well, bach.eval again, tau time log2 time t to the l is the logical time. It comes in input $f1 divided by t plus 2 to the power of v minus v. This is gonna be our time warp operation. This is nice, but then we have to apply an amplitude volume. And the amplitude volume is to be applied according to a central rate. So we have to apply this formula. This could be a sort of a multiplier for the velocity. In order to remodulate the velocity according to a factor, there's a nice abstraction in Cage called cage.volume. We can use that. Well, again, it works in a lambda loop. It spits out the original time. Well, it's gonna be the time in the score, and it expects the amplitude at that time, the amplitude factor at that time. So what we get here is TE, and what we need to get here is PR. The only problem is that we don't have TE in this equation. We have R, but yeah, it doesn't really matter because R is a function of TE, and so we can use this formula, plug it in instead of R, and we get a formula for P according to TE. That's what we are gonna do. So we evaluate this formula. It should be something like exp minus log2. I'll just put R for now. I will change it later. R divided by RC. We know what RC is. To the power of 2. Very well. Divided by 2 times sigma squared. Very good. This is our equation. It works fine, but this equation doesn't know what R is. So we have to tell the equation that R is something. Let's define it beforehand. R is something. What is it? Well, it's 2 to the power of TE is the incoming time divided by tau plus V times T times log 2. Log is the natural logarithm divided by tau again. So this is R and this is our full expression. Now we can compute R and then compute this expression. Well, this will be the only one output because it's the last one. That's how bach.eval works. If we have multiple expressions one after another with semicolons, the last one is used as evaluation result, which is what we want. We compute R and then we compute this. Very well. There can be a final thing we can or cannot do. I mean, we can remap also the frequencies of notes according to the speed rate. So we can simulate a sort of vinyl-like effect. In order to do that, we can maybe use cage.transp. And how would we use it? Well, again, in a lambda fashion, we will change the transposition of the notes according to the speed rate. From the lambda outlet, the time position will be output, and the corresponding transposition in cents is expected here. So what we have here is the time position. We can compute the rate at which the buffer is read. And starting from the rate, we can convert the rate into an actual millicent difference by using bach.r2mc. It's not hard, you can use logarithms for that, but if you don't want to think about that, r2mc is convenient. And the rate is just given by this equation, so we just need to apply again bach.eval 2 to the power of te, again $f1, divided by tau plus v times t times log 2 divided by tau. Here we go. Very good. Here we have the transposition. And we might want to check that things go on smoothly before continuing, because this is most of the thing we had to do. We're almost done. But let's check it works for each one of the layers before closing up things up. So let's put a bach.roll here, and let's put manually an integer value here. For instance, layer number 0. Yeah, this seems pretty much correct. Layer number 1, layer number 2, layer number 3, layer number 4. Well, I'm not sure if you want to have the duration line going up. This could be something you may or may not want. You see, they really correspond not to the article, but to our to this diagram. Okay, so this is layer number 2, and it's actually 1, 2, 3, 4 sawtooth waves. You see them in the notes. That's nice. At the same time, you may not want it because maybe you're writing for piano or for flute, and you really cannot use them. And one thing you can do is to set at dl0, which tells cage.transp not to process duration lines. In this way, we just have, you see, we just have notes processed and not duration lines. And you see that this works quite nicely. 1, 2, 3. And moreover, this works for any score we can put here. So we can use something more complicated than that, such as this. And everything gets sped up, okay? Here we go. Seems to work fine. What do we do now? We need to collect all these layers into separate voices, but that's easy. Let's put a bach.collect at inrep1. So all those rolls are collected. At the end of the UZI, we get all the rolls. And again, we can use cage.combine voices. It used to be called bach.combine voices. It still exists, bach.combine voices, but I advise you to use cage.combine voices. It should be in cage more than in Bach, in a sense. And once we have this, we have the meta bar. Let's put a bang here. I may have done a mistake. Well, let me see. Of course, the mistake is here. We are filling this score, but we are not dumping it. Actually, we don't need to dump it. So nothing comes here in bach collect. We don't need to dump it. We just need to do that. And we don't need this score any longer. It just fills the space in our patch. We don't need it. Let's do that, and let's do that again. And in principle, we should have our voices showing up. Here we go. Yes. You see that this is the first one, the second one, the third one, the fourth, the fifth. Okay. We can change the score. Here we go. You saw that this one and this one were the same, but it was a coincidence because in variable speed rate, this F and this C ended up both to B. But it's not always the case, as you've seen with so we can put something simple like a CDC or something like that to see what happens. Here we go. Another thing we might need to do is to display the score in a better way, let's say. First of all, higher layers could be first and lower layer could be bottom, so we can reverse this list. Let's put back drive 1 to reverse all this list. And then we may want to assign clefs automatically. So let's do something like that. At last, this is one of our meta bars, but we want to repeat it multiple times. So let's do that again. Just put a bach repeat. And how many times do we need to repeat? Well, we need to repeat it just n times. We defined it n here. So let's put a bach eval n and something like that. Well, we can trigger it at any time. It doesn't really matter. Let's do that. So it's clear. And that's pretty much it. And let's see whether this works properly. It does not. It makes a mess. Why does it make a mess? Well, it makes a mess because I've used bach repeat instead of cage repeat. You see, I'm making mistakes again. Cage.repeat, of course, not bach.repeat. Why not? Because bach.repeat repeat LLLs, whereas we want to repeat a score. And whenever you want to repeat a score, rotate a score, slice a score, and so on, it's cage dot something that you need. So let's do that again. And here we go. This is nicer. Okay? This is our Risset-like accelerando of our source rhythm. We can display velocities if we want. So let's go in the inspector and take color scale to show velocities. And we see that actually there's a central rate, which is darker, and then it goes down and down at the bottom and at the top, so that it fits quite nicely with the idea that there's an accelerando at a central rate, and we have this bell-like curve. So there we go. This is our patch. I've just added a bach.easyMidi play here at the bottom to have a feedback. I've deactivated the highlight play attribute because we have so many notes that the playing process would be cluttered just because of redrawing notes one by one. So whenever you have many notes and you need the strictest synchronization, remember to turn highlight play off or to send a real-time one message. That works as well. And there's an additional small portion of patch which does something. I'm not going to tell you what it does. You can discover it by yourself. As an exercise, you may imagine what it does and then try it and see if it's exactly what you supposed. We can try to hear what some of the scores are rendered into. So let's render this one. Let's hear the result. You can have fun modifying the parameters and see whether other things work best for you. Maybe the sigma, maybe we should retouch the RC a little bit to avoid the sensation of restarting whenever the metabar ends. Or let's try some other thing. Let's try a simpler one. and so on. You can have fun modifying most of the things here. And for instance, you may not want to use the modified MIDI sense, but you might want to use the original one, so you can bypass cage transp, of course. That's gonna clutter on the same notes of the original score. You're just gonna have the accelerando effect with the same notes. And that's it. This video was longer than usual, slower than usual, so thanks for bearing with me till now. And a big thank to all our Patreon supporters for supporting the development of Bach. Till next time.